So as I mentioned earlier, well, is the slide advancing? Oh, there we go. I will briefly talk about challenges with additive manufacturing metals, and then share with you some experimental results and some prediction scenarios, and then close with some concluding remarks. Okay, this is not advancing. Okay. Um, so in terms of, so in terms of advantages of additive manufacturing, I think everybody has heard about them quite a bit. For those who are not familiar with the technology, the main advantages are listed on the left side. There has been a lot of interest in this area from both scientists and practitioners, and you can tell that by the number of publications on top. So these years, it's on the order of 17,000 publications on additive manufacturing or 3D printing. It's that many. It's that much interest. Of course, fatigue of additive manufacturing is a small fraction, only 4%, and you can see the number of publications in additive manufacturing is linearly going up, but in fatigue is exponentially going up. The reason is being that defects and surface roughness, those kind of challenges are still preventing this technology to be very useful in fatigue critical applications. So can I go to next slide, please? Oh, all right. Well, let me try my. Okay, so one big challenge is defects, typically lack of fusion defects and porosity. These defects of various sizes and shapes, you can see an overview of the type of defects on the right slide. And a volume fraction of defects varies throughout the geometry. So the fact that there are defects is a challenge, but a bigger challenge is the variability. So even if you think about a thin wall tube, when you make a thin wall tubular specimen, the defects, their volume fraction changes quite a bit over a 2 millimeter thickness. So the variability is the main issue in dealing with defects. There are many, many process parameters in additive manufacturing. Some count close to 200 of them. There are many post-process procedures that can be used. As a result, there is a lot of variations in defect sizes and populations. So for Type 64, depending on what kind of machine, additive manufacturing machine was used to build the material, what kind of heat treatment was conducted, what kind of orientation the build was, you can see the size of defects changing quite a bit. And this is logarithmic scale. So we are talking about not a factor of 2 or 3. We are talking about orders of magnitude difference in the nature of the defects. Surface roughness is another big challenge. When you deal with as-built surface in additive manufacturing, nearly always fatigue fractures start from surface. And this is an example. Surface roughness depends on a variety of factors, including what size powder you start with, including what layer thickness you are using, and a stair-stepping effect, and so on. There are other challenges with additive manufacturing, including residual stresses, because different parts of the component goes through different thermal histories. So residual stresses not only are significant, but again, they are very variable throughout a single part. Anisotropy is oftentimes an issue, and heterogeneity. Different locations of a given part can have different properties, different microstructures, different defect populations, and so on. So there are many process parameters, and this is a big challenge in that you cannot really be very confident or make a very highly reliable component for fatigue critical applications. And that is the reason that in spite of all of this research interest in additive manufacturing, as far as I'm aware, additive manufacturing is still not used in fatigue critical applications, for example, in aerospace industry. Okay, now, because of these variations I talked about, if you look at fatigue performance of just titanium Ti-64, just one single alloy, this is the kind of variation you see in SN diagram, which is tremendous variation of data. So the data could be as bad as what it is here for a process with rough surface finish or as built surface finish and no treatment, all the way up to a process which is machined and not only machined, post-process with HIP, for example, and you can see then the behavior becomes very similar to the wrought metal. Okay, so this is the objective, but there is a long ways going from here to here. So a lot of the current effort on additive manufacturing is this relationship between process, structure, and properties. There is much less work on performance. And the assumption is that good properties result in good performance, not necessarily in additive manufacturing. Because when you go from properties to performance, when you go from a specimen to actual component level, there are a lot of other issues which become important. So when we are generating properties on a specimen, we typically deal with small coupon specimens. In actual components, we have larger parts. In view of the variability I talked about earlier, that's an important issue. When we talk about properties, we usually use smooth specimens. In a part, we usually have a complex geometry that has notches. In coupon specimens, we deal with a smooth surface. In additive manufacturing, we have a rough surface. A lot of the research is done on machining of additive manufactured specimens. But that's not really practical in many applications because that takes away one of the biggest advantages of additive manufacturing, which is building complex geometries. When you have a very complex geometry, if you want to do machining, it's not going to be very practical. So we do have to live with the surface that we obtain from additive manufacturing. The stress state for simple coupon is uniaxial. In reality, we oftentimes multi-axial stresses because when you have a complex structure, multi-axial stress is nearly always there. In coupon test, we deal with constant amplitude loading. In service loading, we typically have variable amplitude loading. In coupon test, we deal with a small variability. In structural components, we have a lot more variability, and also environmental conditions. So these are some big differences. So let me share with you some experimental data. In terms of defects, as I mentioned earlier, there is a big improvement in fatigue life if you can make the size of defects smaller. So if you look at some Ti-64 data in torsion, this is data from one additive manufacturing machine and then another additive manufacturing machine where the defects are much smaller here compared to this one. You see a big difference. And this is the wrought metal. So you can get close to the wrought metal if the machine that you use for additive manufacturing of a specimen or a component has much better optimized performance parameters. In terms of roughness, if you look at this plot, this is roughness versus cycles to failure. For a given stress amplitude, you can see as the roughness decreases, fatigue life significantly improves. The effect of roughness, however, is synergistic with defects because a lot of defects are centered or are close to the surface. So if you look at axial loading or torsion loading, this happens to be for 17.4 stainless steel, you can see I can get similar surface finish. I have two specimens or two batches of specimens, both of them polished to the same surface finish, but one of them has been machined, one of them has not been machined. And you can see the red is for as-built surface, the dashed is for the same polished surface, and then the blue is for machined surface. Because with machining, not only I get good surface finish, I also remove the defects near the surface. Okay, so if we want to get good performance, we cannot just rely on good smooth surface finish, but also removing of the defects from near surface. Post-process parameters or processes like hipping has a big effect. Again, without hipping, you may have a performance like this, but with hipping, you get the green data, which is very close to the rod data. Okay? And similarly for 17.4 stainless steel, the red data are all without hip, the blue data are all with hipping. Damage mechanism can change quite a bit depending on the kind of variations I talked about in terms of defects, in terms of surface roughness, in terms of manufacturing process parameters. For example, in torsion loading, it can be tensile, okay, along tensile plane, or it can be shear along the horizontal plane. But even for a material that doesn't have a lot of defects resulting in shear, the surface finish, the as-built surface, will change that to a tensile mode. So depending on the variations, we need to know what the damage mechanism is because that will have significant implications in the life prediction methodology we will use to predict the life. Okay, so these are some data, fatigue data under axial loading, torsion loading, combined axial torsion loading. Typically, we use 1 mesos when we have combined loads, so you can see data are not correlated very well. If you use the critical plane approach, you can see the data very nicely come together. If it's shear mechanism, you can use a critical plane approach, which is based on shear. If it is a tensile damage mechanism, you can use a critical plane damage, which is based on maximum principal stress, for example. So damage mechanism consideration is an important factor. Again, multi-axial stresses are very important when we are dealing with additive manufactured metals because, again, a lot of the structures that we build with additive manufacturing are complex structures. That's one of the main benefits of additive manufacturing. But with complex structures come multi-axiality of stress. So again, using the right damage parameter is an important factor. So these are data from different stress states. They all come together using a critical plane approach. Similarly for as-built surface and for machine surface. Okay, notch effect is very important, but the notch effect is different in additive manufacturing compared to wrought metals. And the reason is that when we have a notch in a component, in the wrought metal, what drives fatigue failure is the stress concentration of the notch. So if we look at fatigue notch factor, this is for the wrought metal. It increases with life. In other words, there is more notch sensitivity with the notch. Whereas for additive manufacturing, notch sensitivity actually decreases. The reason is that the defects are there. So it's not just the mechanical notch, but the defects that they drive the damage process. But you can take into account the effect of the notch and the gradient of the notch. So if you look at this hole, there is a significant gradient. You can use theory of critical distance along with the right critical plane approach. Again, you can correlate very nicely all the data under different states with or without the notch. At the component level, we have some data from a link from an aircraft engine. And again, with the right damage mechanism and critical plane approach, you can correlate the data nicely from both the component and specimens built on the platform. I'm rushing through a lot of this. I'm just showing you some samples. There are lots of publications with regards to what I'm showing you. So anybody interested can email me. I'll be happy to send you the papers. Okay, so I'd like to talk about predictive modeling in two aspects. First is the material, and second is at the component level. With regards to material, oftentimes we like to be able to predict fatigue performance. In many situations, we do not have fatigue data. Can we predict fatigue performance at the material level? For example, we have known that for many decades in conventional metals and manufacturing, fatigue strength is related to tensile strength. So the higher the tensile strength, the larger the fatigue strength. So we build models, simple models like this that we usually use in mechanical design based on ultimate tensile strength. Similarly, for a strain life, we have predictive models. One of them is shown here, which is only based on hardness. Again, this is all in the absence of fatigue data. Okay, I'm not advocating using of these approaches, but if we do not have fatigue data and we want to get some rough idea of what the performance is, these are the kind of approximations we use. Do they apply to additive manufactured data? Well, here is a plot of fatigue strength versus tensile strength. You see, there is no correlation at all because of all the variability I talked about earlier. Defects, surface roughness, residual stresses, and their variability through the component, you don't really get a correlation between fatigue limit and tensile strength. Unless you classify the data. So we classify the data based on situations where defects or surface roughness do not control fatigue performance. And then the second group of data, these are situations where the surface is smooth, but there are defects. And then the third situation is where you have a rough surface. So when you divide the data in that manner, I had a student who collected hundreds of data from all the literature so far and classified the data in this group. And now you start seeing good correlations. What is shown here is ultimate tensile strength versus hardness. So rather than using ultimate tensile strength, we use hardness. But there is a good correlation between ultimate tensile strength and hardness. Traditionally, we have been using a relationship like this for metals, for steels in particular, but you can see with all of the additive manufactured data, the correlation also works well. So with the group 1 data, where defects or surface roughness does not drive failure, you can see good correlation for fatigue strength at 1,000 cycles versus hardness, and fatigue strength at 1,000,000 cycles versus hardness. Based on that information, you can construct an SN line. And this SN line can result in relatively good predictions. So 82% of the data were within, I cannot see the number there, 33% of the stress. For group 2 data, because defects play a key role, they have to be taken into account. So we use Murakami's method with dealing with defects. And when you do that, again, there is good correlation between fatigue strength at 1,000 cycles and hardness, and then between fatigue strength at 1,000,000 cycles and fatigue strength that you get from hardness and area of the defect. So that has to be taken into account. Again, not bad predictions for only relying on hardness and defect area. And then the third group of data is most challenging. That's where cracks start from surface because of the rough surface. We have not found yet a good method of dealing with that, but when you look at the data, this is all Type 64 fatigue data, this is other metals, you can see a nearly constant slope for all of them. I don't know what exactly the reason is, but that's what the data suggests. These are actual data, okay? So if you use that constant slope, you can again predict fatigue performance. So based on these 2 groups of data, you can have some rough estimates of fatigue performance of AM metals, okay? This is not only for Type 64, but all different metals. Again, these are only approximations. I'm not advocating using them, but if you don't have any fatigue data, if you cannot afford to generate them, if you want to do some quick calculations, this could be useful. All right, now when we go to prediction at the component level, For traditional manufacturing, traditional material, we use the component geometry, the material properties, and applied loading. We typically do FEA analysis, obtain stresses and strains. We feed that into a fatigue analysis and predict life. Does this procedure work for additive manufactured metal? Well, the big assumption here for conventional metal is that the material properties are representative of the material performance at the component level. Again, not so for additive manufacturing, because in additive manufacturing part, the population of defects, even the microstructure, are different throughout the part. So you cannot make the assumption of the material property obtained from a coupon being representative of the additive manufactured part. Okay? So a much better approach, in my opinion, is using fracture mechanics. Using fracture mechanics, you can explicitly deal with defects. So defects can be obtained from non-destructive evaluation, for example, CT scanning, or from process simulation modeling, starting from powder model, melt pool modeling, thermosolid modeling, and then finally going to microstructure that includes the defects. We have started using this approach. There has been some success. The prediction from fracture mechanics is shown in the solid curves, and the data from different types of loading are shown. In some cases, you see relatively good approximations. In some cases, not so much. Okay? The challenge with using fracture mechanics is in terms of crack growth properties. What is typically available in the literature is for long cracks and for mode 1. When we talk about application to additive materials, we are talking about defects, therefore small cracks, and that kind of data is typically not available. And also not just mode 1, but mode 2, mode 3, and mixed mode. We normally don't deal with mixed mode crack growth because at macro scale, when the cracks are longer, usually they turn into mode 1. Even if you have multi-axial loading and you have mixed mode, they usually turn into mode 1. But when you are dealing with the small cracks, that's not the case. You do have to deal with mixed mode behavior. And then phenomena like friction-induced closure become important. Those are usually not important in mode 1 compared to, for example, plasticity-induced closure, but they become very important in mode 2 and mixed mode loading. So this is the research I'm currently working on with my group on a small crack growth. We have used FLA, femtosecond laser ablation, that creates a structure of defects that mimic or are very similar to defects in additive manufacturing. And these are the type of crack growth that you see. Again, these are very small cracks growing, and different phenomena like crack branching and tortuous crack path are present, and we are trying to model these aspects of crack growth for application in a fracture mechanics framework for more robust use of additive manufactured metals. Okay, so how much time do I have? 2 more minutes? Okay, all right. So some very quick concluding remarks. First of all, defects, surface roughness, and their variabilities control fatigue performance of additive manufactured metal. And they are a great hindrance to their use in fatigue critical applications. The great majority of current fatigue research is at the material level, but we need to really think at the performance level of the component. And we should not assume that there is a direct correlation or direct relationship between material performance and fatigue performance at the component level. So robust fatigue life predictions of AM metals really requires to explicitly account for defects, and the only way I know how to do that is fracture mechanics in conjunction with non-destructive evaluation. CT scanning now is very commonly used for additive manufactured metals. So in spite of those challenges, because of the immense interest for both academia and industry in this technology, people realize that fatigue and fracture of these metals is a bottleneck to their use. As a result, there is a great opportunity for fatigue and fracture community to benefit from all of the work that is happening in this area. And people who are working in this area are not just mechanicians and material scientists, but even people from data sciences and computer scientists. Because artificial intelligence and machine learning, those kind of disciplines are coming into play in terms of optimizing, for example, process parameters to produce additive manufactured metals with fewer defects. So there is going to be great benefits, I think, to the fatigue and fracture community from all the research that is being done on additive manufacturing. And of course, the knowledge will also apply to other types of materials that we have been dealing with for many years, like castings that have defects, like welds that do have defects. All right, so because I'm out of time, these are a few areas that current research is going on. I just want to thank my former students and my collaborators who have contributed to this work. And finally, before I end, there was one. I just want to invite you in 6 months to those of you who are interested in multi-axial fatigue and fracture. There is the next conference in New Orleans in US in November.
Well, thank you. Thank you, Professor Ali, for this excellent talk. So we have time for 1 or 2 questions. Anyone wants to? Okay, please.
Okay, I'm wondering if you would agree with me that the challenges that you presented, can we actually convert them into advantages? For example, heterogeneity, anisotropy, to produce architectured microstructure or gradient property materials. Can you comment on that?
Right here. Yes.
Okay. Yeah.
Architectures for functionally graded material like with structure.
Yeah.
So these are some of the benefits. Yes, there is a lot of potential if we can get past the hurdle of the defects and surface roughness and be able to model them. I think there is really great potential for additive manufactured metals. Here, I hope you didn't get the impression that there is all negative about additive manufacturing. I think once we get past through that hurdle, there is really a lot of potential in making very complex structures, functionally graded structures, lightweight structures, which is of a lot of interest to many industries. But we are not there yet. I think still people are trying to compare the behavior with the wrought metals, with the conventional manufacturing. Once we pass through that, I think all the potentials of additive manufacturing will be realized.
Well, I think just for this young man.
Professor, on slide 23, you told that there is no correlation, but then I could not get what do you mean by R equal to -1?
Well, okay, so if you look at fatigue strength versus tensile strength for steels, each data point is one different steel. So there are lots of steels. You see a relatively good correlation. That's the same correlation for additive manufacturing. Do you see any correlation? It's because of all those variabilities I talked about. So once you start dividing data into groups, like I mentioned earlier, then you start seeing correlations.
Okay. So, well, just last line.
My question is very simple. If you have a defect or heterogeneity inside and outside the coupons, do you find difference between how you can evaluate if the problem come from outside or from inside materials? No, because you mentioned you have a roughness, you have inclusions and impurities. But those impurities, if they are located inside the material you're testing, what is the impact if you have more defect inside and a clean surface? No defect on the surface. How you can distinguish the problem?
Yeah, the problem is that many of these issues I talked about in additive manufacturing affect the performance in a synergistic way. So as I showed in one slide, surface roughness and defects really go together. You cannot just look at each of them individually. In conventional materials, that's what we do. We have different procedure how to correct for surface roughness, and we have a different procedure how to deal with defects. But the residual stress, the defects, surface roughness, all of those things are synergistic. So you have to deal with them in that manner.
Okay, so we thank you again, Professor Ali, for this talk. And Professor Ali will be with us during the week, so we can talk with him all the time. So now we move to the parallel sessions. So please attend your sessions, and we move on. Thank you.
No, I cannot. I know some very dirty words. When I was a student, I shared a room with a Jewish Farsi student. So he taught me all the bad words.
All right.
And I will not
I don't know any
repeat
of them.
them.
I don't know any of them.
Of course, you are well educated.